Oké, vandaag gaan we een uitzonderingetje doen op de regel. Normaal wil ik eigenlijk altijd alles zelf vertellen, omdat ik in ieder geval dingen vaak vertel die niet door anderen zijn opgeschreven, waarvan ik mijn eigen conclusies heb gemaakt. Maar ja, bij sommige mensen is het verhaal eigenlijk al af. En waarom zou ik het dan nog vertellen als de ander het al heeft gedaan? Wat hier dadelijk komt is een lezing van Nassim Haramein. Ik weet niet of je die naam wel eens gehoord hebt. Dat is een alternatieve wetenschapper. Alternatief omdat hij zeg maar de paden bewandelt waar de wetenschap op dit moment niet mee bezig is. En dan moet je zeggen, ja, maar is het dan wetenschap? Nou ja, het punt is dat de meeste wetenschap oorspronkelijk alternatieve wetenschap is geweest. Hè? Ik bedoel, er is een tijd geweest dat iemand met theorieën kwam waar de rest van de wereld zei, ja, dat is pure science fiction. Bijvoorbeeld Galileo heeft beweerd dat de aarde rond was, maar de rechthebbende mensen zeiden dat dat onzin is. En dus gold het als alternatief. Nou bleek dat hij achteraf toch gelijk had. En zo zijn er dus heel veel alternatieve wetenschappers geweest. Bijvoorbeeld stringtheorie. Dat werd ook een tijd lang helemaal niet serieus genomen. Terwijl dat nu hartstikke hot is. En zo is dat wat Nassim doet, iets wat niet serieus genomen wordt door de heersende wetenschap. Daarmee wil ik niet zeggen dat wat Nassim beweert ook meteen waar is. Maar het is in ieder geval een andere kijk op hoe de wereld in elkaar zit dan die kijk die ons de hele tijd voorgeschoteld wordt. Een van de problemen die ik met de kijk van de huidige wetenschappers heb, is dat er veel dogmatische dingen in worden gezegd. Ook in de wetenschap wordt heel vaak gezegd van bij bepaalde dingen dat je maar moet aannemen dat het zo is. Hè? Bijvoorbeeld als je vraagt over de Big Bang, dan hebben mensen altijd zoiets van oké, het heelal is ontstaan door de Big Bang. Maar wat was er dan voor de Big Bang? En dan zeggen wetenschappers, ja, die vraag dien je eigenlijk niet te stellen. Ook als ze het zeg maar over het heelal hebben, waar komt het heelal vandaan? Dan gaan ze uitleggen waar het universum vandaan komt. Nou, dat is niet het heelal. Dat is alleen maar dat gedeelte wat wij kunnen zien. En wat daarachter of daarbuiten is, daar wordt eigenlijk niet over gesproken. Wetenschap is dus eigenlijk best beperkend in hun manier van denken. En eigenlijk, wat mij betreft, net zo dogmatisch als het christelijk geloof. Dat houdt niet in dat ik wetenschap niet vertrouw. Er zijn gewoon een aantal dingen waarvan ik zelf heb, het is een model, het is een beschrijving van de natuur, hoe iets werkt. En tot nu toe is het zo dat veel dingen die zeg maar door de wetenschap voorspeld zijn. Hè? Iets is wetenschap op het moment dat je het kunt voorspellen. Op het moment dat je zeg maar zegt, als ik deze aansteker loslaat, dan zal die naar beneden vallen, want er is zwaartekracht. Nou, dat is mijn voorspelling. Mijn voorspelling is dat hij naar beneden valt vanwege de zwaartekracht. En inderdaad, de voorspelling klopte. En als je zeg maar genoeg van dat soort testen uitvoert, dus andere dingen laat vallen, of dit ding laat vallen, hoe meer van die testen zeg maar laten zien dat wat je beweert wel eens zou kunnen kloppen, des te meer kun je zeggen dat dat wetenschap is. Maar zo zijn er dus een aantal dingen in de wetenschap, vooral in de moderne wetenschap, die je niet zomaar 1, 2, 3 kan testen. Hè? Ja, oké. Quantumtheorie er zijn heel veel dingen niet te testen. En als je dan komt bij plekken zoals het ontstaan van het heelal, ja, dan moet ik maar aannemen dat het zo is. Een van de redenen waarom ik moeite heb om in een vliegtuig te stappen, is omdat men zegt dat vliegtuigen de meest veilige middel van vervoer is. Nou, dan weet ik toch dat vliegtuigen af en toe neerstorten. Dus dat is voor mij geen wetenschap. Nou goed, Nassim is dus ook een wetenschapper, maar een alternatieve, of wat heel veel mensen noemen, een pseudowetenschapper. Maar Nassim gaat wel zo ver om zijn theorieën te beschrijven, hij komt met formules aanzetten, hij komt met wiskunde aanzetten, maar als hij het uitlegt aan een groot publiek, dan maakt hij het wel zo visueel dat je ook zonder die formules het wel begrijpt. En vanwege Nassim, maar ook een ander, Marco Roden, heb ik bepaald besloten om toch maar weer eens de natuurkundeboeken op te pakken. Want ja, ondanks dat hij die dingen beweert en het allemaal wel plausibel klinkt, tot een bepaald punt, hoor, want hij gelooft ook dat piramides machines zijn van buitenaardse wezens. Maar oké, er zijn daarnaast nog heel veel andere fundamentele dingen waar je wel direct wat aan hebt, die wel ja, goed klinken, maar ook eigenlijk heel erg passen in de manier waarop ik zelf naar de wereld kijk. Het is allemaal theoretisch en het is ook leuk. En zelfs als het allemaal onzin blijkt te zijn, dan nog zou ik George Lucas willen aanraden om zijn theorie op te kopen, want je kunt er echt een fantastische Indiana Jones film van maken. Dus zelfs als je denkt van, het is niks van mij, ik zou er toch naar kijken. Echt een fantastisch verhaal hoe de wereld in elkaar zit. Maar zoals ik al zei, ik heb dus die natuurkundeboeken weer opgepakt. Ik heb een cursus gevolgd, die heet Physics for Future Presidents. Dat is een cursus die door Caltech wordt gegeven. En het is eigenlijk gewoon opnames in de klas, in de klas van de universiteit. Dus er staat een professor met 6 borden en er zitten 400 studenten in. En de bedoeling was oorspronkelijk van, als je student was en je had zo'n lecture gemist, dan kon je hem achteraf terugkijken op video. En toen hebben ze besloten van, weet je wat, dit is zo interessant voor iedereen. We geven het vrij op YouTube. En dus nu kan iedereen het volgen. En als je die 13 lessen van een uur volgt, heb je eigenlijk een compleet semester op de universiteit gedaan. En ik heb dat gedaan. En dus ik weet nu wat meer over wat temperatuur is, wat zwaartekracht is. Ik wist al die dingen wel, maar de fijne puntjes. En daardoor kan ik nu ook met mijn hand op mijn hart zeggen dat in ieder geval wat Nassim Haramein beweert, wel een solide basis heeft. Het is dus niet echt uit zijn duim gezogen van, ach, ik pak hier wat en ik pak daar wat en ik gooi dat door elkaar en ik verzin er een paar spirituele woorden bij en hier is mijn theorie. Nee, er zit echt een goede basis achter. En of hij nou gelijk heeft of niet, dat is alleen maar iets wat de tijd ons kan vertellen. En misschien dat over 100 jaar iedereen Nassim Haramein zegt, zoals Einstein. Maar misschien ook dat iedereen hem vergeten is. Dus ja, verder. Hij heeft het dus over de grote universele theorie. De manier die eigenlijk alles verklaart van waarom het universum er is. Hoe het universum werkt, waar materie vandaan komt. En eigenlijk hoe en waarom dit is. En dat vertelt hij, zeg maar, met modellen en wiskundige vormen. En toch heel begrijpelijk. Dus je hoeft eigenlijk geen wiskunde gehad te hebben. Ikzelf, ik had een 4 bij wiskunde op de MAVO. Ik begrijp waar hij het over heeft. Dat zegt genoeg. Hij wordt dus niet door de wetenschap erkend, maar dat niet alleen. Hij wordt doodgezwegen. Dat is echt iets heel fouts. Het is namelijk zo dat er bijvoorbeeld, ondanks dat Nassim Haramein echt over de wereld heen trekt en zeg maar elke week wel in een zaal staat om zijn les te geven en al 3 dvd's uit heeft en al 4 boeken uit heeft, staat er absoluut niks over Nassim Haramein op de Wikipedia. Je kan hem niet vinden. Er zijn wel mensen die een stukje over hem hebben geschreven, maar die stukjes zijn allemaal verwijderd. Nou, dit is heel raar. Het is dus iemand die heel veel mensen heeft bereikt. Die zeg maar in een bepaalde sferen best veel bekendheid geniet. En toch staat hij niet op de Wikipedia. als dat nou zou zijn omdat men vindt dat die onzin vertegenwoordigt, dan zouden dus alle mensen die dingen hadden gedaan die onzin of slecht waren, ook niet op de Wikipedia staan. Maar als ik Adolf Hitler intyp, vind ik hem wel. Als ik Jezus vind, waarvan een hoop mensen geloven dat het waar is en andere mensen niet, dan vind ik Jezus ook. Ik vind zelfs dat Jezus over het water heeft gelopen. Maar ik vind dus niet dat Nassim Haramein zegt dat het universum eigenlijk een groot zwart gat is. En dat vind ik heel erg raar. En dat is een van de redenen waarom ik dit hier plaats. Maar goed, ik hou verder mijn bek. Ik zou zeggen genieten. Hier komt Nassim.
Thank you so much. Thank you for having me. Appreciate. It's great to be here. My presentation today is called The Cosmological Constant and the Schwarzschild Proton, the Energy of the Future. And, you know, don't panic. It might sound a little complicated, but we actually are going to do a little math together today. You guys ready? Good. It's going to be really, really simple stuff, but it has profound implications. So, in order to understand energy, I mean, people use that word all the time. And, you know, actually, if you look in physics, the concept of energy is not so clear. That is, it's nebulous. It's a concept that's used all the time in our equations to make things even out, to make things work. When work has been done by this system, then the energy is transferred to this system. And then if this system does work, it's transferred back to this system, and so on. And those concepts are called conservation laws, or conservation of energy. So energy and conservation of energy. I'd like to read a few things. These are quotes. They're typical. If you open physics books and you look up energy and conservation laws, you'll find these. And they usually go this way. Energy can be defined as the capacity to do work. It may exist in a variety of form and may be transformed from one type of energy to another. However, these energy transformations are constrained by a fundamental principle, the conservation of energy principle. Excuse my reading. It's my second language, and I'm highly dyslexic. One way to state this principle is energy can neither be created nor destroyed. Another approach is to say that the total energy of an isolated system remains constant. This is very important because let's take a look at the deeper definition. If a system does not interact with its environment in any way, then certain mechanical properties of the system cannot change. These quantities are said to be conserved, and the conservation laws which result can be considered to be the most fundamental principles of mechanics. In mechanics, examples of conserved quantities are energy, momentum, angular momentum. The conservation laws are exact for an isolated system. And, you know, these are laws that have been in place for some 100 years. And we've been using them everywhere in physics. They are fundamental. Yet, most people ignore or pass over, and children are not shown this when they're taught these laws. Students are never taught to go back and look at it more carefully. There's one, you know, very important concept in these laws that come out every time, and it's the concept of an isolated system. So you have to look up isolated system. And when you do, you can be quite surprised. An isolated system implies a collection of matter which does not interact with the rest of the universe at all. Okay? And as far as we know, there are really no such system. There is no shield against gravity. The electromagnetic force is infinite in range. But in order to focus on basic principle, it is useful to postulate such a system to clarify the nature of physical law. And here I have a bubble, you know. All natural laws are based on something that is not found in nature. You'd think there'd be a problem there. In particular, conservation laws can be presumed to be exact when referring to an isolated system, which we just define as not existing anywhere in nature. So how exact are those laws? So there lies the problem. The idea that things can be isolated, that you can, you know, put something in a box and assume that you can analyze that thing ignoring everything else that's going on in the universe. As if you've isolated that box from the rest of existence. And more, as we advance in our technology and in our physics, we realize that that is just not the case, that that is not actually anything that exists in nature, and this artificial way of analysis does not lead to accurate description of the physics of our universe. So how do we deal with it? In one way, what we have to do is start to get what I call a holistic view of the universe. The whole thing. We got to start with a concept in which we understand the whole structure a little more before we start looking at the part. That is, we got to make we got to have a clearer picture on how the structure of embedded system exists in our universe before we try to identify what the part may look like. Otherwise, it's similar to like taking a Boeing 747 and breaking it down to the smallest piece and then giving that piece, which might be very tiny, right, to an engineer and saying to the engineer, okay, what did that piece come out of? Could be problematic. He might come up with like a pink elephant. And so, this isolated system is really a problem. Let's look at it in a different way. Let's take a look at it in a geometric way. We can call this an isolated system, right? We have a circle that obviously isolates the space within it from the space outside of it. But is it truly isolated? When we look at this, if we look very closely, let's say this was a dot, a little teeny point, and we look really, really closely, we might start to see discreteness in it. We might start to see structure in it. So in this case, let's make the structure an equilateral triangle. And let's polarize that. And as soon as we did, we got a fundamental recursiveness to the geometry we started it with. We have the same triangles that could produce new horizons, new boundaries, new so-called isolated systems. And in each cases, each of these isolated systems is going to observe the rest of the geometry from its own very perspective. So we could say that every point in here, every new boundary is a new set of information, right? Since it's individually observing the rest of the system from its own very specific perspective, gathering its own very specific information, yet having the same geometry and being part of a larger system, which is the whole of the system. You all following me? So in physics, information can be equivalent to energy. So as each time that I'm making a new division, I could say that the energy of the system is increasing, that there is new information being generated. So here, further boundary conditions are generated, and these can be polarized and get further boundary conditions, and so on, and so on, and so on. And I can continue to do this to this system towards infinity. If I give this to my computer, it will continue to make divisions. I could get him to zoom and then keep dividing and zoom and keep dividing and so on to infinity. I would never, ever, ever get to the end of it. However, I would never, ever, 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 ever exceed that first boundary I've started with. So I here can show that infinite amount of information, infinite amount of discreteness, infinite amount of energy can be present in the so-called confine of an isolated system, in the so-called confine of a finite boundary. And then if I zoomed out from that boundary, I would see that that boundary is most likely embedded into a larger one, and into a larger one, and into a larger one, and into a larger one, so on, to infinity. So I have infinite fractal divisions from infinitely small to infinitely big. And in a system as such, there would be no lack of energy, since there would be infinite amount of information from any boundary conditions that I picked. So this leads to the realization that if we were to write new physics that assume open systems, relationships, then that system most likely would start looking, those physics most likely would start looking like fractal physics, holographic physics, in which all points are in relationship with all other points. All information is present in each part. And taking this view, if I was to look at something like a hydroelectric dam, and I applied the open system conservation law to a hydroelectric dam, I would get something different than what we get today. For instance, today, in conservation law, if we have a lake and there's water coming down that lake into a turbine, oh, bad turbine. Okay, kind of a turbine. And we got plus, minus. And here we have a gravitational potential, right? The water is elevated relative to the turbine. gravitational potential. And the gravitational potential is given to the turbine in terms of spin, the stiction and friction. Because of conservation law, we will only extract a very small percentage of, a small percentage of the available gravitational potential, and that will be transferred to electrical power here. Okay? However, the water comes out of the turbine, and in current isolated system conservation law, that's where the box ends. But today, we're going to break the box. So, if we break the box, then we follow the water. And as we follow the water, we realize, wow, it's flowing south. Because the earth is spinning, and because the sun is shining, and because there is, Coriolis forces, the water that's flowing south is evaporating in clouds. And these clouds that are south, because of Coriolis effect, are coming back north. And when they get up there, it's cold and it snows and rains, and it goes back into my lake. And that was free. I didn't have to pay for that part. Nowhere in the universe is there a toll booth that's, asking you to, that's charging your credit card every month to make sure your atoms keep spinning. That would suck. Because they spin really fast, it'd be really expensive. So nature is giving us all the power we have today already. Right? At its most fundamental level, this is given. It is already free energy, if you'd like. What we need to figure out is how to extract it at its source. How to extract it before it's produced the material world. Because if we can get to the source of energy, the source of the energetic universe, and we live in an extremely energetic universe. Look at, there's galaxies, there's stars, quasars, even the surface of the sun, it's extremely energetic there. It's not dead. We're flying through space at thousands of miles per minute. And there is people on this planet in their isolated system saying, wow, there's not enough energy for everybody. So how do we get to the source of it? First, we got to ask the question. If we look at that system, if I look closely, I would say, but wait, if I keep dividing to infinity, what am I dividing? What is the substance that's being divided? And that leads to the question, what's connecting all these scales? It leads to the question, if I give you all the things in the universe, everything, you got the whole universe, and I said to you, okay, point at something that connects all things. Find me something that's everywhere. You'd have to think about it for a little while, and then you'd eventually go, oh, space. Space is everywhere, right? Space is in between galaxies, between quasars, between pulsars, between stars, between planets, between atoms. in the densest material on Earth, like carbon, like diamond, if you took one of the atom in the diamond molecule and you grew it to the size of an orange, the other orange would be 2 football fields away. That's how much space there is in the material world. Actually, and many spiritual people say, oh, it's so dense over here. Nah, not really dense. And actually, these were the last words of Buckminster Fuller on his deathbed. It's like, he realized, and I'm sorry to say that, but nothing touches. Like for your partner, that might be a problem, but nothing has ever touched anything. Atoms are very far away from each other. When I touch this podium, my atoms in my hand are not anywhere close to touching the atoms in this podium. If they did, there'd be fusion, there'd be all sorts of gamma ray emission, there'd be some serious issues. There's large distances at those scales. All that's happening is that there's a little electromagnetic field here that's not in phase with this little electromagnetic field, so can't get through it. But if those were in phase with those, my hand would go right through it. No problem. Question of phase. But as well, if we look even deeper than the molecular structure, if we look at the atomic level, then we find that the atom itself is made out of 99.9999999% space. Mostly space. The material world we live in is space with a little jiggle, 0.00001% that we pay a lot of attention to. That is the little jiggle that we call reality, the real world. Physicists told me one day after one of my presentations that I didn't live in reality. And I said, thank you very much. Because we're made of vacuum. And, it appeared to me early on when I studied a little physics in high school that, wow, maybe it's the other way around. Maybe it's not matter that defines the space, but maybe matter is defined by the space. Maybe it's the space that defines the atomic structure. Maybe the medium is space, and the atom is just a little division, a little oscillation of that space. Maybe space is what connects all things. Maybe space is what organizes everything. Because that's a problem in physics. The incredible organization we see in nature everywhere is not trivial. It really isn't. You can't just account for it by random functions. It doesn't add up. If you do the math, it doesn't work. If the universe was random, in 13.7 billion years since the Big Bang, we wouldn't even have a little blade of grass with all the little microbial life and DNA and all this stuff in it. That would be too complex. Let's go back to our jumbo jet. It'd be equivalent, actually, it'd be easier to take a jumbo jet into its smallest bits again, and let's not freak out the engineer this time. Take all the bits, there would be a lot of bits, and threw them up in the air, and assuming that by the time it comes back down, it's a functioning airplane. It doesn't add up. In your body right now, the organization that's going on every second is like so remarkable. There's like 100 billion chemical changes occurring per second. There's like DNA, so that if I took all your DNA and unraveled it, like when you pull on the thread of a sweater, and I unraveled it and pulled it out of you, what's contained in you right now, I could wrap around the world 5 million times. I can go from the sun to Pluto and back to the sun and back to Pluto and back to the sun, back to Pluto and back to the sun with your DNA. And it's functioning perfectly well. It knows exactly what it's doing. It's not confused at any moment, because if it were, even for a few instants, it would be a really bad day. Really, really bad. Very quickly. But it's highly organized, and really in science today, both in physics and in biology, there is no explanation for this. We, for instance, in physics, have no clue how systems self-organize. All our theories are based on entropy, are based on systems, isolated systems, that have entropic behavior, conservation. That is, a system always go, according to our current physics, towards further disorder. However, you might have noticed in your bedroom yourself, for most of us, where there is disorder in our bedroom, they must have been order before. If we see systems that are moving towards disorder, the question, begs the question, where did the order come from? Because if it's going towards disorder, then there must be some fundamental principle of order present. And actually, when we look at the natural world, we see it go towards higher and higher level of complexity and higher level of organization. And we see negentropy. And that negentropy, the water going back into the clouds and raining back into our lake, that's the part we want. That's the part we want to understand. That's where the energy would be. That's where all the information of all organization would be. This is what we want to tap into. This is what we want to log on. It'd be the ultimate hard drive. Right? And as we identify, that might be the space. If that was true, if space would be that thing that organizes all things, since it's in contact with everything it could, if space is the holographic metric that creates systems, then that space could not be empty. Space would have to be full of energy, full of information. It wouldn't just be a little bit full, it would be infinitely full. Is space infinitely full of energy? Most likely. But how? I start to then look in physics where we would have evidence that space is not empty. Where we would have evidence that space is something other than nothing. Could we be that confused about something that looks like nothing? Well, it wouldn't be the first time. For instance, when the first equations for electromagnetism were rendered, there was some evidence that there was, more than the visible spectrum. But it looked like nothing to everybody else. And it wasn't until a photographic plate was left near radiating material that it was discovered that, whoa, we have X-rays and da-da-da. Oh, there's other frequencies, there's other things, radio waves, infrared, and so on, past what we see, what we experience directly with our 5 little senses. And today you don't think about it twice. You turn a radio on, you tune it, and all of a sudden a voice comes out of there. And all that programming is in the space. I go to physics conference, and many physicists, it's now the trend. It didn't used to be 20 years ago. If you said the C word in a physics conference, you'd get kicked out, The C word being consciousness. But now, things are changing. It's the cool thing. If you're retired or if you're looking for consciousness or the relationship of consciousness to physics. And many of these professionals are looking in the brain. This is equivalent to taking the radio set at home, opening it up, and looking for the announcer. It's not in there. It's just tuned. It's a resonance match. And that resonance match is a match to the structure of the vacuum itself. So I started looking at what the vacuum is doing physically, what is the space doing physically that I could quantify to see if it's really there. And, eventually I was in physics conference, and one of the physics conference I was at, I stopped everybody in the middle of a discussion about string theory, so we were in 11 dimensions of superstring, and knots were flying everywhere, and all this stuff. We were trying to figure out if a knot was really knotted or if it was not, and, we were getting very confused. And, at one point I stopped everybody and I said, hey, I've been looking for an equation. You guys are all so awesome in physics. I'm sure you guys have an equation for this, but I'm not finding it. I've been looking for 15 years. I really would like to know where it is. And he said, okay, what is it? And I said, well, if I understand our current models of physics, the universe at the cosmological level is expanding, and the model we are given most of the time is a balloon with pennies glued to it. So I pulled up a physics book and showed that. And the pennies are glued to the surface of the balloon, and they represent galaxies. And as the balloon expands, the galaxies move away from each other. I shouldn't do that because my profile, my nose gets kind of blocked. But these galaxies moving away from each other is a representation of the expansion of the universe. And when I said to them, the equation I cannot find, I really would like some help on that, is what I want to know is who's this guy? I can't find the equation for it. I saw the director of the Department of Physics there getting a little nervous, and I didn't get the same reaction for some reason. one of the PhD students started to choke on his coffee, and I think they thought I was going to say the word God in the physics department, you know. Please don't go there kind of deal, you know. And so I said, well, let's draw the rest of the guy. Maybe we'll get a clue because I'm not getting answers. Notice that when the universe is expanding, the lungs in the guy have to contract. For every action, there's an equal and opposite reaction. Some of the first laws of physics we learn. You know, in these moments in physics, usually they're followed by quiet time. And usually somebody's saying, isn't it time for lunch? Or, so how's your wife doing? So what I was pointing out there is that the space in the balloon has to have some physical meaning. The vacuum cannot be empty. It has to have a capacity to expand that balloon, and that is the collapsing of the vacuum itself. That is, that we only observe the radiative side of creation, and we call that the material world, but the vacuum, the space, has a physical function that may be the collapse that produce this expansion, that they may be a feedback, and that this function is not explored by us. We miss it, because, sorry to say, but our evolution and our society is mostly male-oriented, which is that radiative, you know, everything is like, let's blow shit up. You want to go somewhere, baby? Let's take some of that explosive material over here, put it in a cylinder, have a piston, boom, 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 wheels are going to go, we're out of here. You want to go to the moon? Let's build a nice phallic symbol. Fill it full of highly, highly explosive material. Thousands of tons of the stuff. Put a little capsule on top. Find volunteers. Put them in there. Light the bottom and run. And since it's not very tantric, you know, within a few minutes, like, there's a little ejaculation. So, maybe there's a different approach. Maybe the vacuum structure, maybe the space is the counterpart. Maybe in the space, which seems to be the force that's expanding our universe, and since this moment, you know, we found that not only is our universe expanding, but it's accelerating. So in order for that to happen, they had to put energy in the vacuum called dark energy or the cosmological constant. And they had to add this energy to the vacuum to make it expand. So now we know there's definitely energy in the vacuum, and we can measure it. So that's at the cosmological level. Now let's look at the subatomic and atomic level. Oh my God. I got to go faster. At the atomic level, I realized, reading physics, that, oh my God, they had found energy in the vacuum, and not just a little bit. Let's read it together. Present-day quantum field theory gets rid by renormalization process of an energy density in the vacuum that would formerly be infinite if not removed by renormalization. That is, when we looked at the atom in, almost 100 years ago, and we start to calculate all the oscillations that would occur in space-time, in the structure of space inside the atom, in the 99.99999% and around the atom, we found that if we got close enough to the structure of space-time, it would be fluctuating with infinite amount of modes. That is, there's infinite amount of wavelengths that you can find smaller and smaller and smaller and smaller and smaller and smaller wavelengths to infinity. That's what the equations were saying. There's infinite amount of energy in the vacuum. And, when I found this, I'm like, they actually found it. They found the structure of the connectivity of all things. They found the structure of the vacuum. But that was not their realization at the time. They said, oh my God. It was called the vacuum catastrophe. We got to get rid of this infinity. It's infinitely big. Ours said, wow, we found the source of creation, infinite amount of energy. Wow, how do we get in there? No. Instead, we renormalized it, which is okay, when you're writing equations. But it's not so much the renormalization that's the problem, is that it was renormalized and then it was placed in the closets of physics for almost 100 years, until people many different inventors throughout the ages and people like other researchers and I started to talk about this and make this forefront. But how did they renormalize? What they did is they used a constant called the Planck's distance. The Planck's distance is a calculation that's very valid as far as I can find. And certainly in my latest paper that I'm going to show at the end of this presentation, it's remarkable. And the thoughts right now is that the Planck's distance is the smallest thing the universe can do. It's the smallest oscillation of the structure of the electromagnetic field that can occur. You can think of it as a photon going through itself, or the time it takes for a photon to go across its radius, or its diameter. So you can imagine it's teeny, it's really, really small. It's 10 to the minus 33. That's like, that's like a period with 33 zeros, right? That's a lot of zeros before you get a 1. It's really, really small. Now, do I think it's the smallest thing the universe does? Absolutely not. But I think that the Planck's distance is a very important scale for our relationship to our current size universe. That is, it defines a boundary level at the smallest, and the universe boundary defines the boundary level at the biggest, and that gives us, a relationship in our scale. You guys follow? So I think it's an important thing. So what they did, I know the little Shanti dog wants to come up here and give some physics, but always get excited on this part, doesn't it? So what they did is they took little Planck's distances and they said, how many of those can we stack in a centimeter cube of space? And since each one of them is a little energy, right? It's a little oscillation. E equals mc squared can tell you how much the mass of that oscillation is going to be. And the mass is 10 to the minus 5, so it's very small mass. However, if you count all the masses of all the Planck's length in this centimeter cube of space, you'll get a density. How many mass per centimeter cube is there in the vacuum oscillations? And the answer is 10 to the 93 grams per centimeter cube. 10 to the 93 grams per centimeter cube. That is a big number. Okay? That is a really, really big number. You might have noticed in your bank account, you know, when you have like zeros, you keep putting new zeros, it improves rapidly. You know, if you have 3 zeros, you add another one, it's like, oh, nice, you know. You add another one, oh, yeah, no, that was good. No. You add another one, oh, yeah, now we're talking, right? So imagine you got like 93 of those, right? Things are looking good, right? Now let me give you an idea of what that number really means. If you took a centimeter cube of space and in it you squashed all the atoms in the universe, all the stars, in all the galaxies, there's billions of galaxies, each one has billions of stars in it, and squished them all into a centimeter cube of space, you would have a density in that cube. Imagine how dense that thing would be, right? You'd have a density of 10 to the 55th grams per centimeter cube. 10 to the 55th grams per centimeter cube. That is very large already, but it's 39 orders of magnitude less than the density of the vacuum, which is 10 to the 93 grams per centimeter cube. All right? You're swimming in an infinite soup of energy. You're most likely living off it. When you eat, you actually are replacing vacuum energy that you've desecrated. You are feeding off the vacuum literally, and you could actually bypass the eating part. And that has been shown. I've done it myself. And, you know, nowadays there's sadhus in India that are coming out of the woodworks to be examined by the medical establishments, and they're being isolated in a room for like months at a time. They don't drink, they don't eat, they don't defecate, they don't sweat. They live directly off the vacuum. And, you know, that's a being. Imagine that you got a technology to pull out of the vacuum. If we got 1/1000th of a billionth of a billionth of a billionth of a percent of what's there out, we would have enough energy to run the whole planet for thousands of years. Never mind the capacity to curve space-time, create space drive, overcome gravity, get off the surface, which we really, really, really need to do really, really soon, and so on. So, if this is true, we should be able to measure it in laboratory. In 1947, because you might say, well, yeah, that's all nice, but it's just equations. Maybe you guys are lost. Well, in 1947, a guy called Casimir, a physicist called Casimir, said, well, we should be able to measure it. If that's true, we should be able to get plates close enough together so we can eliminate the long wavelengths and just remain the short wavelengths between the plates. The result would be there would be more energy outside, less energy inside, and the plates should get pushed together, create a little gradient in the vacuum. When he did the calculation, he realized, wow, the plates have to be really, really close together, microns apart. Nobody could mill plates with micron precision in 1947. It took until the 90s before this happened. And in the 90s, when it did, then the plates got pushed exactly as was predicted by Casimir. The experiment was reproduced in laboratories all around the world, and now we even have results of a dynamic Casimir effect, or Unruh effect, and that actually pretty well proves unequivocally that the vacuum is there, and that it has physical meaning, because almost for 100 years, they said that this vacuum energy is way too big, and it probably has no physical meaning. I think it's the foundation of all physical meaning. And that's a big difference. So, it really is there. Now, if this is true as well, then when we look at the universe, if they're basically just division of the vacuum, then all the pieces in the universe should be in harmonic relationship to each other. They should be some coherence in the way the vacuum divides, if the vacuum connects all things. And so, with the help of Dr. Rauscher, we wrote a scaling law to see if that was true. We started, and the scaling law is radius against frequency, or you could think of it as radius against energy, and we started with the universe. Now, I would like to let you know that if you take the mass of our universe as we observe it today, and you stick it in a bubble in our universe that we see our universe size to be today, the universe obeys the Schwarzschild condition. It obeys the condition of a black hole. We live inside a black hole. That is, if I shine a laser light in the night sky tonight, okay, well, maybe during the day, the light ray is going to get bent a little bit by the gravitational field of the sun. And it's going to go for a while, and then it's going to hit another star, and it's going to start bending a little more. And it's going to hit more stars, and it's going to bend a little more, and so on, and so on, and so on. And there's too much stuff in our universe that light will not be able to escape it. We live inside a black hole. Did you know that? So if you live inside a black hole, which has this, this infinity inherently in it, then you'd expect, maybe I'll get that there's a thing there, maybe you'll expect that little smaller things along that line will be just smaller divisions, smaller black holes, smaller singularity. And if they line up, they would be. So here's quasar. We know they're black holes. Here's the center of galaxies, all galaxies. We know they're black holes. From this theory, I was able to predict that we were going to find a black hole at the center of all galaxies. I got in a lot of trouble for saying that some 25 years ago. But now we found black holes at the center of all galaxies. As well, I was able to predict that the black hole at the center of the galaxy is present before the galactic formation. That is the source of the galaxy, not the result, which was the assumption that was made in the Standard Model, that the black hole in the center of galaxies was the result of all the stars colliding there and making a black hole. What I was saying is, no, the black hole is there first. That's what's producing the matter that we see as a galaxy. It's a continuous creation model instead of like one big bang, which is more of the male approach, And so, then stellar objects, many star-sized objects are black holes, and then we jump from stellar objects all the way to the atomic structure. And that in physics is not expected, because currently we think that cosmological objects are dealt with classical physics, or at least Einsteinian physics, and the atomic structure is dealt with quantum physics, and the two don't agree. And most physicists will tell you they're not related. Yet, you know, they might have not noticed, but big things are made out of small things. So obviously, they must be related, right? Now, so here we jump all the way to the atom, and the atom falls almost perfectly on this line. Remarkable. And then all the way to the Planck's distance. You see how far the Planck's distance is compared to the atom? Imagine how teeny that is. That's the atom. You see, there's less distance between a star and an atom than between an atom and the Planck's distance. So you can imagine that's a huge scale from the universe to the Planck's distance. The odds of all these data points falling on that line are extremely low. Yet they do. If we lived in a random universe, these data points would be all over the place. So, is everything in the universe a Schwarzschild black hole? Is everything in the universe just smaller division of singularity? Singularity comes from the word singular. One. Are we only observing division of the one? Wow, this is starting to sound a lot like ancient texts and, you know, all these prophets and all these masters that have walked the earth that told us that. Maybe we should have tried applying that to physics. Yeah. But if this is true, there's a problem. This guy. Well, atoms are not thought to be black holes. So how is the atom a black hole? If you say to a physicist today, an atom is a black hole, he'll say, absolutely not. The atom is not massive enough to be a singularity. Okay, how do we deal with mass? Yes, indeed. If we look at the bottom, at the confine of physics today, the standard model has zero explanation from what mass is. We don't have a clue. We have a model that says that it's related to the Higgs mechanism, the Higgs boson, which is our current model, and, you know, is quite controversial. And in any case, that model says that the Higgs boson is a fluctuation of the vacuum itself. So, and, you know, CERN, and this is why we built the Hadron Collider, the largest accelerator ever built. $13 billion later, 17-mile long, coils so large that the first time they turned them on, they ripped off the anchors, went flying into the tunnel, and embedded themselves into the detectors. The whole thing flooded with liquid helium, and they had to evacuate. So $2 billion later, they turn it on, but it's so wide and so long of, you know, a device to maintain that some bird had placed a little crumb in the wrong place. Poof! You know? Looking for the Higgs boson, which is now seeming to not be found. In any case, what I said is, hey, are we ignoring the vacuum? Yes, we are. So if we looked at a proton, and this was in the paper, the Schwarzschild proton, that was published 2 years ago. It was published at the CASI conference in Belgium, the one I just came back from. This was the 2009 CASI conference. It received the first paper award there. I was very, very surprised because it's very controversial. Thank you. And there's been discrepancies of internet chatter about that prize. It is peer-reviewed, and it is peer-reviewed by professional physicists. And so what I did is I took the volume of this little proton, and I said, how many Planck's distances fits in it? That is, how many of these little oscillations of the vacuum are in there? Because we're not counting those. So we should count those when we're talking about the mass of the proton. We can't just ignore that. So I outputted the volume of the proton. 10 to the minus 39 is its volume. And I said, okay, in that volume, how many little Planck spheres can I stick in there? And the result is 10 to the 55, which happens to be the mass of the universe. And when that came out, I was blown away. Because I had been saying for all this time that the vacuum is the great connector, that the energy in the vacuum structure is what holds all the information, what connects every point with every other point. That means that every proton, which is the nuclei of an atom, the center of the atom, should have all the information of all other protons in the universe. And that's exactly what happened when I wrote the equation. So I was like, so excited. I was actually so excited I thought I'd mention it in the Schwarzschild proton paper. I just put one sentence. I didn't want to say this is a mathematical proof that everything is one, but I put this may be evidence that all protons are entangled through the structure of the vacuum. So, but do I need 10 to the 55 grams per centimeter per proton volume for the proton to be a black hole? Absolutely not. 10 to the 55 grams is enough to make the whole universe a black hole. So that is not correct. It cannot, well, you know, it definitely makes the proton a black hole, but what I wanted to know is how much of that energy is actually expressed in the dynamic of the proton for it to be a black hole. So in order to do that, I had to use the Schwarzschild equation. Do not panic. Don't run out the doors. It's not going to hurt. Maybe just a little, but then it's okay. It's a simple equation where the radius of the system is equal, so the radius of the black hole is equal to 2 multiplied by the gravitational constant multiplied by the mass over the speed of light squared. And this is a consequence of Einstein field equation. This was the first solution to Einstein general relativity equations. It was written by Carl Schwarzschild. After Einstein published general relativity, he hadn't solved it. He thought it would take a very long time before it got solved. Carl Schwarzschild looked at it and came up with this solution, this exact solution, and sent it back to Einstein and said, your general relativity theory predicts singularity, predicts a black hole. That's the solution for a black hole. And you know, Einstein was unhappy about that result. He thought, you know, oh my God, my equation predicts something that probably doesn't exist. At the time, the idea that black holes would exist, you know, or singularities, the word black hole was not even coined. That was John Wheeler much later. They thought it was just a mathematical point, not a real point. But they realized, I mean, eventually Einstein's general relativity got sustained by experiments and by, you know, observation. So, you know, they realized it was useful. So this equation actually is used, for instance, to figure out the orbits of the sun and the moon. Right? They do the Schwarzschild solution for the sun. So basically, and that's important, they reduce the sun to a black hole. Okay? That is, the radius of the sun becomes 18 kilometers, or approximately that, for a black hole. And then they write the equation, and they get the correct orbit for the Earth around the sun. But then they don't turn around and say the sun is a black hole. Right? So, however, that's the equation they use. You can imagine that maybe, just maybe, there's a layer of the sun, okay, that's the plasma we see all around the sun, and that inside it's collapsed into a black hole. And we would never know. Although, we would know if we thought about it, because the equation we'd use to solve the orbits would be a black hole equation. You guys are following me? So I use that, but in this case, I know what the radius of the proton is, so I'm not trying to figure out the radius, I'm trying to figure out, in such a radius, how much mass do I need for it to be a black hole? So I had to change it around. This is the way it is, right? Over there, so mass is unknown. But I wanted to know mass. So I had to flip the things around, and I got the result. I don't have time to give you the details. I'm sure you're all interested in them. The result is 10 to the 14 grams proton. And that makes the proton a black hole. And if you actually figure out how much of the vacuum energy you've used from the 10 to the 55, you've used 10 to the minus 39% of what's there. So you've used teeny weeny little bitty little amount of the amount of energy of the vacuum to produce all the protons in the universe. Just a little teeny weeny billionth of a percent to produce all of the matter in the universe. So imagine if we tap that resource, which we can. Which we are, as you are alive, tapping it right now. Now, if you say this to a physicist, you're going to encounter a large objection. An objection of about 38 orders of magnitude. The physicist is going to say, you got a proton of 10 to 14 grams. The measured mass of the proton is 10 to the minus 24. You're off by some 38 orders of magnitude, dude. So, how do we resolve that? I mean, when I came across that, I knew when I got 10 to 14, okay, it's not the standard mass of the proton. How do we resolve that? It took me a while, and then I realized the key is the strong force, dear one. What is the strong force? When we found protons, we found that they were positively charged and that they would repel, just like two magnets of the same charge would tend to repel. And if they're strongly magnetized, you can't get them close together. So imagine protons squished in a little nucleon atom with the same charge. How can that be possible? When we found that, we were like, oh. And since we didn't have black holes, Einstein had just finished his equation that predicted singularity, but everybody thought that's impossible, right? They said, okay, they must, and so gravity could not be strong enough. We didn't have singularity black holes. So they said, oh, there must be a force we don't know about. We'll call it the strong force. And we'll make it exactly the amount of force necessary to force the proton together into the nuclei. How convenient. But nowhere was it given as a mechanism of this force. That is, where did this force come from? Where did the energy come from to produce that force? It was just thrown in there as a fudge factor to squish the atom nuclei into existence. Later on, and they calculated it had to be very, very strong. Later on, they realized that the proton has little bits inside it that are even smaller, called quarks. And now the quarks are charged, so they now needed an even stronger force to squish the quarks into the middle. Now that's embarrassing. You can't call it the strong force. So they got artistic. They called it the color force. And so the color force was deemed to be infinitely strong at the quarks level. Like that, you know, if they found anything smaller, they had infinitely strong force to deal with it. And that this strong, infinitely strong color force was mediating force to the proton level using gluon particles. Gluon. So that's when I asked, who's making the glue? Because nowhere in this whole scheme did they say where the energy come from to produce an infinitely strong force. But if you have an infinitely strong force confining to the center of a particle, what do you have? A black hole. Right? So, I said, okay, since latex QCD doesn't give, you know, gives computational results and no analytical results, which is the way they deal with the scheme of the strong force. If you ask a physicist, how strong is the strong force, they'll say, we can give you a ratio. If gravity is 1, then the strong force is, guess what, 38 to 39 times stronger. Exactly how much my proton is off by. Right? So I said, well, you know, in my case, I'm accounting for the energy necessary to produce the gravitational force that confines the atom. You guys don't. So obviously, you guys are off by 38 orders of magnitude. It's not me, it's you. However, I knew that wasn't gonna, you know, go far. So I figured I'd give them a scaling law to see if I'm right or they're right. So I made a scale between the radius of an object and its mass, the radius and its mass. And I put the universe, and I put everything I could throw in there, like local clusters, galactic centers, galaxies, whole galaxies, galactic cores, pulsars, the whole thing, the sun. I mean, I threw the Earth in there. I mean, the whole thing, to get like as accurate of a trend as possible. And then I put in the Schwarzschild proton mass. And it fell very nicely along that line with all the other objects. And then I put the standard proton mass. And that was the only data point off the chart, literally. And so that confirmed, in some ways, that obviously the Schwarzschild proton is realistic relative to all the rest of the universe, and that's straight data. It's not out of equations. So, but when I did this and when I published it, I knew there was going to be some controversy about it. Why? Because the universe here is the universal mass is calculated by adding all the standard protons' mass. So that mass is the result of all the standard protons' mass added together. If that was the correct mass, then the universal mass would be off the chart, and all the data points on it would be off the trend. You all following this? So that was a problem. And, you know, I knew that was a problem. When I published the Schwarzschild proton paper, I didn't claim that it was complete. It was just an impetus in one direction. What was really wonderful, however, is that when I looked at the black hole protons, if I orbit them around each other, I got many of the data you get from the standard model. Like I got the correct gamma ray emission, I got the correct interaction time, I got the correct magnetic moment, I got all this stuff correct, so I knew it's correct, but I had to solve this. How is it that it can express two different masses? And this is what I just solved. This is what I just published. And the result is like way beyond my greatest expectations. So I'm going to show you what I did. The first thing that happened, it was middle of last year. I said, okay, well, we have a little proton that has 10 to the 55th grams in it, the mass of the universe in it. And you know, it may be, if this is true, if it's the true holographic representation of all the other protons in the universe, this may be the first time we get an exact number for the mass of the universe. And I knew there was this big problem in physics. It's a problem that's part of the vacuum catastrophe. That's 102 orders of magnitude problem. 122 orders of magnitude problem. And that's because, remember I was saying that that the universe has this dark energy in it that's inflating the universe. The vacuum has this energy in it at the cosmological level. When the physicists calculated the density of that energy at the cosmological level, they found that it was 10 to the minus 29 grams per centimeter cube. All right? So it's a really, really teeny amount of energy per 30 minutes. Okay. And at the quantum level, it's 10 to the 93. So it's a huge difference. If the vacuum has 10 to the 93 grams per centimeter cube at the quantum level, how is it that we're measuring 10 to the minus 29 grams at the cosmological level? And there's 122 orders of magnitude different. That's huge. That is currently the largest problem in physics ever encountered. It's commonly referred as the worst prediction physics has ever done. Okay? And if you look up on Wikipedia, for instance, problems in physics, I think it's the first, the vacuum catastrophe, 122 orders of magnitude problem. Well, I solved that in an instant. Sorry, but I did. About a year ago, when I realized, wait, I've got a 10 to the 55th gram proton that is a result of the 10 to the 93 grams per centimeter cube density of the vacuum, okay? And so per proton volume, right? And what happens if I grow that thing to the size of the universe? Obviously, the density is going to drop. So I grew it to the size of the universe, and my result was 10 to the 30th gram, minus 30th gram per centimeter cube, really close to the measured cosmological constant. So I was like, wow, it actually works. And you know, in physics, this would be close enough that you could say, well, I'm going to adjust the size of the universe till I get the right number for the measured value. And that's going to give me a prediction for the size of the universe, right? Which we don't know. There's a wobble between, it's between 10 to the minus, 10 to the 27 to 10 to the 29. So 10 to the 28 is usually the value that's given. But it's rough, obviously, because it's cosmological. So I said, well, how can I get a real number? Because I could have adjusted it, but I didn't want to cherry pick. I had been given hell for the last 2 years on the internet, you know, by all my critics saying, he's cherry picking. So in this paper, I was like, no cherry picking. There will be no cherry picking. Forget cherries. And so on. So I said, okay, well, I know the mass of the universe since this should be accurate. If it's accurate, if I do the Schwarzschild condition of that mass, right? Remember that equation? If I solve that equation, it'll give me a radius for the black hole universe. Let's see if I do the same thing with that radius. This would be the first time we get an exact radius for the universe. So I did that, and when I grew it, boom, 10 to the minus 29 grams per centimeter cube. I was like, okay, this works. This works. And again, if this is correct, this is the first time we know the exact mass and the exact size of our universe. So I said, wow, you know, this is showing so much evidence of the holographic principle of this concept that from studying the proton, I can actually understand the whole universe. I should look at the holographic principle and apply it. The holographic principle in physics is utilized to describe the entropy of black holes. That would be the amount of thermodynamics that come off a black hole. You could think of it in Kelvin. And what is currently used is that they map little Planck's distance on the surface event horizon of the black hole and then count them and make this calculation and they get the entropy of a black hole. I started to think this way. I started to apply that. So I said, okay, it's holographic. Let's look at relationship. I took the Planck's distance. I knew it was I made it a surface, and I plastered it over the surface of the event horizon of the black hole proton. But when I plastered it, I took the surface area of the proton, right? And I divided it by the number, by the area of the Planck's distance little circle. So it has to be space filling. That means the circles cannot be one beside each other like that, because if they were, there would be little spaces in between. It has to be space filling. You guys follow me? So when I said, well, how could they be space filling? Well, guess what I got? The flower of life symbol. And I thought, wow, you know, if it comes out, I'm gonna shit my pants. I almost did. I almost did. Because what I did is I said, okay, how many of those is there? Those are all little Planck's oscillations, right? And there's 10 to the 40th of them. So there's a lot. And I said, okay, out of those, remember in the middle is all the little Planck spheres, right? See, these are little Planck spheres in the middle in 3D that are projecting onto the surface. That is the holographic principle. You guys saw that? Do it again? Okay. That's actually the beginning of the movie Black Hole that Guyam just released about the research I'm doing. So let me try to, oh, I missed it. Let me do it again, just so it's clear. So inside the volume of the little proton, right, is all the Planck spheres, right? That's how I got the 10 to the 55th, right? So this are all the little Planck spheres. Here you see tetrahedrons because they tiled, if they produce the flower of life structure, they tiled just like tetrahedron structures. And that's where the work I'm doing links with the work that Richard Hoagland is doing and others in hyperdimensional physics. Because that is the structure of the vacuum, right? And so I said, okay, these spheres are projecting the information of the whole universe onto the surface. So they must, so it's a projection onto the surface, which is the holographic principle. And then we're going to see why the surface has less than the interior in a minute. But you see here, it's projecting onto the surface. That's what I was trying to show here. Okay? And it's a curved surface. It's the surface of the event horizon. So when I did that, then ooh, it's slow for most people. I'm going to write here. So what I did is I took the number of little circles on the surface, right? All the circles on the surface. That's 10 to the 40th. Can everybody see this? 10 to the 40th. And then the number inside is 10 to the 55th, right? It's the mass of the universe. Basically, divide the number of little Planck surfaces by the mass of the universe, okay? And what I got was exactly, what I got was exactly R sub S, the Schwarzschild mass. 10 to the 14. 10 to the 14, which is the Schwarzschild equation. I have the Schwarzschild equation here. Gravity outputted completely geometrically. No curvature of space-time. You know, no geodesics. Just pixelation of the structure of the vacuum itself. This is quantum gravity that I've been looking for all these years. And the solution is exact, okay? Exact only if the tessellation is space-filling, the flower of life. Under the paw of the food dogs is a sphere with the flower of life tessellated over the surface. The guardian of the knowledge. Then I said, okay, if this is really cool, if this is true, I should be able to continue to do relationship in there and get all sorts of information about our universe. So I took the number of Planck's surfaces, 10 to the 40th, but this time I divided it by 10 to the minus 39, which is the volume, proton volume. The volume of the proton itself, instead of the number of Plancks in there. And the result was 10 to the 79. And when 10 to the 79 came out, I recognized it right away. I said, oh, this is really close to the estimated amount of particles in the universe. Right? We know there's approximately between 10 to the 78 to 10 to the 80th or 10 to the 81 amount of particles in the universe. And so, if this is true, this would be the first time we have an exact number for the actual amount of particles, right? Well, you can think of like protons, right? Most of the universe is hydrogen atom with one proton, so in general, just protons are counted in our universe. So just you could think of the amount of atoms in the universe, if you'd like. So I thought, well, this would be cool if this is exact. So then I did something a little weird. But, you know, I have those moments. I did something a little weird that I'm going to show you I rectified right after, but it gave me the right answer anyway. But I said, okay, each one of these little circles is like a little micro wormhole connecting all the protons, all the Planck's length in the universe with all the other protons. The reason why I thought that way is because that discrepancy between the standard mass and the Schwarzschild mass, I kept on seeing in my head and in my work, in my philosophy, that it's because you can't just look at the mass of one proton because it's influenced by all the other protons in the universe, right? Remember, it's not isolated. So if it's linked, okay, I said, okay, then I got to divide the Schwarzschild condition by all the other protons to see what would be the influence of a proton on one little Planck's distance. So that's what I did. I divided the number of Planck's distances, right, by the number, I divided the mass, the Schwarzschild mass, by the number of protons in the universe I was getting. And that gave me the standard mass of the proton, meaning when I divided the two, it gave me 10 to the minus 69, which would be the 10 to the minus 65. So that would be the influence of one universal proton, another proton, on one little Planck distance. You all following me? Connected through that one wormhole, right? So that every internal structure of every proton in the universe is all one thing connected through these wormholes, right? So I was looking for the influence of one point of contact, one wormhole. And that gave me 10 to the minus 65. And then I said, okay, let's multiply all those together, all the little wormholes together, the influence of all the other protons, because we're looking at the proton from the outside. And the result is when I multiplied the two, I got the exact mass of the proton, the standard mass of the proton. 10 to the minus 24. I was blown away. I was blown away because it was extremely exact. I mean, it's 0.019% exact, which is inside the measurement error in laboratory, so this is actually most likely the exact mass of the universe, of the proton. But think about it. I could have skipped that step, since I know the amount of protons in the universe, assuming that this 10 to the 79 is correct. I should be able to just divide it by the mass of the universe. That would tell me how much each proton weighs, right? And when I did, it came out exactly right. This is the mass of the universe extrapolated from the inside of the proton and divided by the number of protons in the universe extrapolated by the surface, and I got exactly the mass of the proton, which was like incredible, because you gotta see what I saw there. You've got a huge number, 10 to the 80th, right? 10 to the 79. And you're dividing by another huge number, the mass of the universe, and you're nailing 10 to the minus 24 grams, teeny weeny proton, exactly right. Unbelievable. Unbelievable. One too many proton in there, and this is off. A little too much mass in the universe, and that number is off. But it gets it right on the button. So this cannot be, random. And I've solved this, and this is actually in a second paper I'm about to publish. I've solved this in a much more classical way now. I've got this equation that's like m equals mc squared type that everybody is going to be able to solve with a calculator, any students in high school. Anyway, it's super simple. It's a clear relationship, and that's going to come out soon. Thank you. Thank you. But even more important is that this ancient symbol that's found all around the world, that was so important to so many ancient civilizations that they made sure that it would survive all spans of time to reach us today, seems to be the exact solution to the holographic universe, giving us the exact correct answers, and that is remarkable. As well, that leads to a deeper understanding on how we would build technology to reproduce those dynamics in laboratory so that we can access this energy. Now we understand quantum gravity. We understand that gravity is basically just a ratio of information to surface area. And that actually this surface area interaction, you see, there's 10 to the 40th little Planck's termination of wormholes on the surface, but there's 10 to the 80th particles. So how is it that one is connected to 10 to the 80th if it's only got 10 to the 40th possible connection? Well, that's because when you, it's not only holographic, but it's fractal in nature. That is, one little proton is connected to 10 to the 40th particles, and these 10 to the 40th particles are connected to 10 to the 40th particles, and so on. So that you have this fractal progression, that you can identify. And this is actually why I called my theory 25 years ago the holofractal graphic theory. Is because it's holographic and fractal in nature. And I knew it was in there somewhere, but I finally mathematically solved it. The other thing that's really exciting about this is that this is the yardstick. We can apply that to infinitely big. You know how the Freemasons have that that compass symbol as the symbol of the yardstick of the universe, the geometry of the universe, God's, scale? Well, this is what we've got. Meaning that I can now tell you, from studying the proton, this little teeny bitty thing, the mass of the universe, the cosmological constant, the energy of our universe, the size of it, right? The gravitational field, but not only that, I can tell you how many of our universes there is in a larger one. And what is their energy level? And what's the energy level of that larger universe? And what's its scale? And all sorts of information. And then I can tell you how many of those larger universes there is in the larger one. And again, and again. So now we have the fractal yardstick and the network connection so that we can actually navigate our universe and the multiverse we live in. We're on our way. We're on our way, folks. This is leading to very advanced technology. I can't believe how long it takes. They drop you off on this faraway planet, in this faraway galaxy, and then they tell you, well, you got to make it home, with local available material. This leads us to technological development, and we need your support for this because we need laboratory, we need funding to get it done, and that's on its way. But please support us. Please become members of the Resonance Project Foundation so this can continue. But thank you. As well, you can get a 4 DVD set right behind us. That really helps us. This pays the bill and the light, and the Black Hole DVD as well, that's out. But in any case, you can see that now knowing this, you would want to create an environment in laboratory where the oscillations of the vacuum inside the bubble would be in correct relationship to the vacuum oscillation outside the bubble. And when you got the right ratios, and when you got the right spin rates, because these little surfaces, they're little vortices, right? When you get like Coriolis vortices, when you got the right relationship with the right spin rate, you should get singularity. You should get, gravity in a box, right? So early on, in early laboratory tests, I built technologies to reproduce these dynamics. And to reproduce the dynamics of a black hole in a laboratory, you can imagine that you would need plasma spinning at high velocity and all this. But when you got it done, it would be extremely stable. And you could alter the spin rate to create various effects. And these are some of the experiments we're in process of doing. This was my talk for today. And I wanted to just say, although all this seems very technical and it seems very, mechanical, maybe, it has so much deeper meaning and deeper implication for our understanding of ourselves, the universe, and the dynamics that connects us all. You can actually when I solved these equations a few months ago, I've been meditating since I'm 11. I've been thinking about this stuff all my life. I got a deeper, new level of the interconnectivity of all the atoms of my body. They all had these moments where I felt like the wormhole linking to the whole thing. It's like, My God. And this is available to you. This sense of connectivity, this experience of connectivity through the structure of the vacuum. Never forget that you are 99.99999% energy of the vacuum, and that is actually informing you every second, and you have access to it. This is why all the masters have asked everyone to spend the time every day, even if it's a few minutes, to turn your senses inward and go to that point. Go to that point of singularity. And connect with the whole, connect with the holographic nature of all the universe, and be the infinite being that you are. So until next time, may the vacuum be with you. Thank you so much. Thank you. Thank you. Thank you, I appreciate. Thank you. Thank you so much. Thank you. Thank you. Thank you.